All right, so I'm starting I'm going to start the crazy and start in order here. See how far we get. We won't get to it all, but I definitely want to get through some of these with you. And what I don't get through with you, I'll post another video online so that you'll be able to hopefully go through all of the multiple choice. Also, hopefully go over the part 2 with me. I'm also planning to be here Wednesday, 9 through 12, and Friday, 9 through 12, no Monday. Okay, so that's 6 more hours with the tall person, if you'd like. Okay, so being crazy and starting in order, we've got this reaction, classic way they set you up. Notice, as I've mentioned before, they're never going to give you oxidation potentials, they give you reduction potentials. So one of these two have to flip. Okay, now the key to this problem was saying that a student uses a galvanic cell to determine the concentration of ethanol. Okay, so if I'm using a galvanic cell, it's another word, Luigi Galvani. Remember, he was the one with the frogs that he was shocking, okay? And there was Alessandro Volta. He was the guy that said, no, it's not, this electrical shock moving the legs isn't just a biological thing. And they had that argument, okay, that's what I told you. And Alessandro Volta proved to Luigi Galvani that, in fact, it's a physical process of the universe that this is working or that biology is using. The bottom line is the galvanic cell is the battery. So uses a galvanic cell. It's the electrolytic cell that you would need a battery to make happen. Since we're not talking about connecting these reactions to a battery, you should have realized that I needed to produce a positive voltage here. Okay? So I need to produce a positive voltage. So that alone, if you think about it, if I was to flip this second one, okay, you would see that's negative 1.2. So all of that setup should have led you to believe that I need to create a spontaneous positive volt half reaction here that gives me that. So right away, knowing that I need that and knowing that there's no battery connected, and they didn't say the word electrolytic cell, electricity involved, I knew that, okay, that this was going to reduce, stay that way, because if I flip this one, okay, I certainly could make it positive. And I certainly, so let's look at this. So we want to create a scenario where we're producing, or at least looking at this methanol. So essentially, I'm going to take this reaction here, and I'm going to flip it. Okay? And I know that that becomes the opposite. That means that these electrons are on the product side, and that becomes what? Oxidation. Okay? All right, so that becomes my positive value. Make that smaller. Okay, so this becomes my oxidation half cell. This is written as reduction. And if you look, calculate the E of cell. Okay, all I'm going to do is add these together. Okay, very simple. 9 plus 5 is what? 4. Okay, 8 plus 2 is 10 and 11. And I get 1.314. volts. Now, a lot of you guys didn't write the units. Make sure you do. Don't get lazy. It's a voltage. Okay? And now, of course, how do I get the overall reaction? Okay, so let's do some whiting out here. This is not how you would do it on a test. You would go to the answer booklet, right, Sam? Okay? And not write the entire test in between the lines. Okay? Well, because the lines were just places if you wanted to doodle in between the questions. All right? You didn't have enough time, okay? All right, so any case, so flipping the first, I get what? C2, H5, OH.
The smartest kid in the class, so you can't figure that out.
Okay? He wasn't alone.
I know, I did too.
I did.
Yes.
I did.
I didn't get a 5.
Because I've been doing with everyone else. I'm sorry, so I felt bad.
Yeah,
Listen,
this one
I spent the last 20 hours grading these, so yeah.
Crazy.
Great times. Okay?
Why is
I wanted you guys to have this.
Fantastic.
Mr. Grassi, I'm so sorry. Number 2, I literally wrote it above the whole entire question, drew an arrow. Like, I don't know why I did that.
Like I said, good times. Okay, so the O2 is written as such. So O2 is going to be, we flipped the first one. And then, of course, we always flip for chemicals, don't we? Plus, let's put the arrow here.
Ice cream for ice cream.
Yes, 4 H pluses. And then, of course, I've got 4 electrons. I'm really writing this out of order, but I feel bad. Now I'm over it. And this was 12 electrons. Let's get this stuff out of the way. Didn't like that, the wheel of death. So I won't do that. Okay, it did not like that. It did not like that. It said no to me, is right. We have 12 electrons.
No, Mr. Krusty.
This is 4, and of course this makes 2 H2Os. Okay. So what are we going to do here, party people? And I know some people didn't do this very well. It's tough drawing a straight line this morning.
Multiply by trace.
Yes, you got to balance the what?
The electron.
When you balance your charge, you balance the reaction. So I've got 12 electrons on top 4. So I'm going to distribute a 3. 3 times 4 is 12 electrons. 3 times 4 is 12 protons. 3 times this is 3. 3 times 2 is 6. And if you notice, we're going to cancel the electrons off on both sides. We cancel off the protons, and then we just add together. So basically you get your C2H5OH. Oh yeah, and now listen, some people did leave 3 H2O, 6 waters. That would be fine, but you should realize that the 3 waters go bye-bye here, okay? And now you have 3 left. So that's the reaction. One of these, no waters, 3 O2. Of course, that now. So if I write that, it'd be C2H5OH plus the 3 O2 molecules gives me the 3 remaining water molecules plus what? 2 CO2s. And now what they give you, my friends, they gave you 2 points. They gave you point for the correct reactants, which means you flipped this appropriately. Then they give you another point for balancing appropriately. Some of you guys don't give up on the problem. You had this flipped, but I gave you a point for having it balanced in any fashion that was somewhat correct.
So what? They get 2 points. That was
So 2-point part to that. Yes.
They would do that.
At least they did it in this test. You don't know how they're going to do it, so don't give up. Don't say, just keep going. Try to throw something there. So this is a point for the correct reactants and products, a point for correct balancing, and then a point for the voltage, which in my opinion goes together. All right? And most people did okay with that, okay? So let's go to the second part. Well, this is actually the third if it's the letter C here. So let's go to C. Maybe see my way out of this.
Okay. Oh my god.
Okay, so they gave you a 10 milliliter sample of the ethanol. It's put into electrochemical cell. Okay, Mrs. DeGradsky, it sounds like electrolytic cell. No, no. Electrochemical cell could be the battery, which is a voltaic or galvanic cell because of the argument of Luigi Galvani, Alessandro Volta. Okay, and it could be electrolytic cell. Electrochemical cell is just a redox cell, so that doesn't tell you anything. But it tells you it produces a current. So this was screaming to you, what?
Wow, man.
It was screaming to you that what we just did was a battery, was positive voltage. You should have set that up. So C was giving you that hint as well. But this is easy right here. They gave you a current of 0.10 amps. What is an amp? They give you this awful I equals what? I equals what? Q over T thing? I think that's awful. Okay, what is an amp? An amperage is amount of current. Current is charge. So really what an amp is Coulomb per second. It's the amount 1 Coulomb per second. Now, they want the charge that pass through the cells. The first thing I do is because an amperage is per second, how many seconds do I have?
I don't know.
20. So if I've got 20 seconds and there are, okay, in this case the amperage is 0.1 amps. So what does that mean? There is in this case, it's 0.1 coulombs per second. So if there are 20 seconds, how do I figure out total coulombs? Right, by multiplying your amperage by the seconds. Now, in other problems we've had, if I've had an electrochemical cell on for an hour, we converted that to minutes to seconds, and then we would times, okay, by the coulombs to get total charge, and then maybe Faraday's constant to go to moles of electrons, which is coming up shortly. But the point here, all this was 0.1 times what? 20. Okay? So you should have gotten what? What's the 10% of 20? 2. So basically 0.1, so I would take my, I don't even know how to set this up. You shouldn't be spending a lot of time here, but this is 0.1 times 20. Okay, and why does it work? Because 20 seconds would what? Cancel out here. And you get 2 coulombs. That was a point.
I'm still like, what are coulombs?
Coulombs is the amount of charge that gets pushed or pulled along in the battery. The battery's voltage is a pathway based upon how well the one who oxidizes pushes the current and how one who reduces pulls the current. So the voltage is the force in an electrochemical cell. The current is the actual charges being pushed around. Okay, so you can have low current, high voltage, and as I said before, you have a waterfall. That's the what? That's the voltage. A voltage on electrochemical cells tells us how much current can be forced around. Higher the voltage, higher the energy. Okay, so that was a point there. Now they want the initial concentration. Okay, so how do I know? How do I figure this out? Okay, well, if I know that. We know that 20 seconds, all of this had to be consumed. That's the key here. Okay, it took how many coulombs to consume that?
2.
So I've got to take my charge and I've got to convert that into how much stuff was consumed. So what's the key here? Faraday's constant. Why is Faraday's constant the key here? Because I'm going to convert my charge into moles of charge, of electrons. And once I have moles of electrons, I can connect that to what?
Polarity.
To, well, the half reactions above. Okay? Okay, I don't know where this pen went. But that's what this is. We keep practicing. We've seen this before, yes?
Yes.
So that's why we keep going. So you have to practice. You may not have seen it for a while, so I'm going to get rid of some of this.
I always get so jealous when you can do that in like your lectures and stuff, and I'm like, I wish I could do that.
Oh yeah, no, he does it on his lectures, and then I'm like, my whole page is filled.
Like when we did like titrations, you would like
Yeah, especially-
X out like a huge chunk. I was like,
Okay. I feel bad now I'm over.
that's
So now,
okay.
I'm going to take my 2 coulombs. Now, I want to find 2 coulombs, and guess what? I want to get rid of coulombs. Coulombs goes in the bottom, and what do I know? What is my Faraday's constant given to me?
96500.
965.
85.
Oh,
No, 96485.
96.
Me and Hunter were the
50.
Well, Hunter
No,
was
Okay,
the
coulombs. That's the charge per
96485.
1 mole of electrons. Did I round? Good enough.
Yeah, you rounded.
That's fine. Okay, so this will give me moles of electrons. Now, my friends in chemistry, great, but how can I use it? Well, back to the what?
Backtrack.
Backtrack in the half reaction.
Back to the half
Okay.
reaction. Up there goes the moles of
Okay,
electrons.
there's what? 12 electrons. That makes my what?
1 mole.
Yeah.
Right, so in my half reaction, okay,
Squiddy.
I have 12 electrons that are being what? Pulled away to make the current. So I'm going to take, this gives me moles of electrons. And what am I going to do with that?
Divided by
Right, I know that per
12.
half reaction, and this is why I look at a half reaction, I know there are moles of electrons. Well, guess what? I know that there are 12 electrons per 1 C2H5OH. I am using, and this is classic, guys, you'll see this again, I'm sure. I'm using this from the half reaction, not the balanced overall, just that half reaction. So what does this give me? This gives me now moles of this. And the last piece, to
Divide
find
by
molarity, I divide by what?
Wait, how do you know it's the
0.1.
C2H5?
Because they're saying they want the
Oh, yeah,
initial
yeah.
amount of this. This, there was 12.
Okay.
Okay, so I'm going to find moles of this, and now I'm going to divide by, just like we do acid and base, the initial concentration of the volume, which is 10 milliliters, that becomes 0.1 liters.
So like that with the one C2H5OH, that's like a unit of like moles, right? You treat that as moles for like cancellation.
Right, I've got total what? Total coulombs in my 20 seconds. That was the charge that the battery produced because that is the electrons that came out of the what? Out of this alcohol.
Yeah, yeah, yeah.
So remember, it produced a charge because this thing got oxidized. This produced 12 electrons. So the current was produced by the one who oxidized. So find the total charge. we found that in the time period, times by the amperage, divided by Faraday's constant, I got moles of electrons. Great. And I know there's 12 of these per one of these. And that's what I'm doing here. Now I've got this, divide by 0.1, and I have my molarity. Molarity is moles of your substance over what?
Liters.
Right. By the way, some people would say, some people might say to me, okay, some people might say to me, Mr. Grazi, how did I know that I should be talking over voices, guys. How did I know I wanted molarity? Look at this. Brackets means molarity. So this is 0.1. Okay? So whatever that value is, and of course,
0.01.
okay, so you get 0.01 is correct because it was 10 milliliters. Thank you. Okay? So in any case, what do I get? I get a molarity that is approximately equal to 1.7 times 10 to the negative 4. They give you a point for this right here. They give you a point for getting the total moles needed,
They give you one
and then they give you a point for the molarity. So 2 points there.
They give you
Okay?
one point.
Have we done a problem quite like this?
Yes.
Yes, but was it exactly like this?
No.
No. So it was. So this was a very, very, I would say, creative way to take a electrolytic cell and do this with something that's not being plated. We've seen it with plating, but again, same skills. Okay, moving forward. Okay, now we have the spectrophotometer. I don't even read any of this stuff.
Yeah, wait, I was going to ask you that. Those long paragraphs, what do you suggest?
I'm going to go right to the question.
Okay, because usually I just underline
Because
all the
sometimes
numbers.
you're just saying how this set up, how the spectrophotometer is calibrated.
Bless you.
We've done all that.
Yeah.
Okay? So here they want to know what the concentration of the substance that has a color, okay, at 1.5 minutes. Okay, now, that is not the absorbance. The absorbance is the ratio of the light, okay, that made it to the detector. It's the ratio of substance, the light missing, right, over the total light. So as the absorbance increases, the concentration is the highest. As the stuff reacts, it starts going from color to colorless. Okay, so the missing light depletes. So they want the concentration. Now, we haven't spent a lot of time with this, but we had two spectrophotometry type of labs, and the formula given to you is A, crazy, equals ABC. Now, A is the absorbance. All right? B is the path length. Now, the path length is how much light goes through that cuvette that we were using.
0.5.
Okay, in this case, it was 0.5. We used cuvettes that were 1 centimeter, so that became a 1. And this C is the concentration. It's a concentration that we usually calibrate first. Okay, so I could solve for this. Okay, knowing A, knowing this 0.5, all I would need is something called the absorbent constant. Now, did they give that to me? Okay, do I have that up here somewhere? Okay. A solution, concentration, initial concentration. The solution has a strong acid, keeps essentially throughout the place. Has path length and place absorbance, so it's set at this. Okay, and it does not give me the absorbance constant, does it? But what it does give me, it has an initial concentration of this, okay, which is what we're talking about at an initial concentration of that. Okay, so we're talking about this chemical, right? So the concentration of the C2O7 is 1 times 10 to the negative 3. Originally. So here's what I'm going to do. I know the absorbance, right? I know the absorbance at 0. I know the C. I know the path length is what? 0.5. I solve for my constant. Now once I have that, right? Now I have a different absorbance. I just have this constant. I have this as 0.5. I can solve for C. Or, okay, some people did what? Yes?
Use the absorbance for 40 nanometers.
I'm not sure how the nanometers would help you.
I don't know. I did that. And
I'm not sure that because this could be set to measure any wavelength. It's not really what the wavelength with a watch is. Yes?
Could you do the absorbance over the
absorbance over the concentration still equals this constant times B.
Because I did absorbance over concentration is equal to absorbance over concentration.
Yeah, that's what I did.
Okay, so, alright, so what you did essentially was, you saw essentially how these concentrations were changing over time. So you did a proportion. So what they did was they saw, okay, if this, assuming that this was constant, okay, you did a proportion which would work out as well. So you could have seen how this changes with time, okay? And that worked, and it worked out because this was pretty linear. But the best way, okay, would be to solve the absorbance constant first, okay, and go forward. But yes, you could have done a proportion to see, hey, if it's at this time period, and now what would it be? You certainly could make that change, assuming it's linear. It was linear, okay? So basically, what I would have went through is said, okay, A equals A plus B. The absorbance was, let's make that in red because I'm tall, 0.782. It's equal to my A. So I'm going to solve for A. So this should go BC underneath, right?
Yeah.
Right? A equals ABC, a tough one, right?
It was
Okay. You never thought you'd be doing that in AP Chem, right? So that would be A is over BC. Okay, so what's B is the path length, which is 0.5. And then, of course, the C is my concentration, which is 0.003, correct? Oh, it's 0.001. So if I put this in my calculator to find my absorbance constant, just showing you how to do this, this is the way that I believe you should be doing it, because you can't assume that line's going to be constant. Didn't we do this, lab? Something like it?
Yeah.
Was it linear? No, so you can't always assume that. It worked in your flavor for that question. Good point. But this could be a multiple choice question, guys. Divide by 0.5 times 0.001, close the parentheses. And if I'm not mistaken, I get 1564 for that. So that gives me my absorbance constant is 1564. Okay, now I'm ready to rock and roll. So now doing this here. Sorry if you can't do that. I feel bad and I'm over it. So now I know what? A equals ABC. I'm trying to find what? My C. So C is equal to what? My absorbance over AB. I know what AB is. Okay, I think I need more space, so sorry. Okay. So what do we have? A absorbance at 150 is 0.553. And it's over A, which we found to be 1564. I'm leaving out units, guys, for those purists out there because it's a time factor here. And my path length is now what? 0.5. And that would equal my C, which is my concentration. So very clearly 0.553 divided by 1564 times 0.5. And I get the answer, let's put that in magenta, because I'm feeling it, is 7.07 times 10 to the negative 4. Okay. And they gave me a what? A point for that? Yeah, a lot of work it feels like, but rock on. Okay, so next question. Student runs a second trial, but this time uses a cuvette path that's twice as long. So the cuvette's twice as long, which means there's going to be what? Twice as much light going through that substance. So there's going to be twice as much light missing. That's what the absorbance is how much light is missing. More light missing, more absorbance. More absorbance, more stuff. So if I use a cuvette now, it's twice as long, okay, then I'm going to have what? Twice as much absorbance. The light's going to hit twice as much more of the chemical. So, describe how this experiment should be adjusted to keep the absorbance constant. Double the concentration. Now, in truth, this isn't perfect because there is some point where the light isn't going to quite pick up twice as much. There's a limiting factor to that. It's an inverse square law in terms of the effect of light, but assuming it's bright enough to do that. Yes?
I said that increased concentration, but I didn't say double.
I have to reread to see exactly what you said. But in any case, the idea here is that you have to pump it up a lot. Okay. saying double is fine. Justify with respect to factors that influence the absorbance sample. Well, what affects A equals ABC? The constant's going to stay the same. The path length depends on A. And I guess if you think about it, I guess that's the reason why they're not accepting it. A equals what? A, B, C. So if you were to keep the concentration of what? Same, okay, if you were to double the path length, B, and you want to keep this the same, you're going to have something, which is C. So they're definitely looking there. Because of this relationship, they were seeing that you understood that this was an inverse relationship based on the formula. So you had to say half based on this. We're assuming the spectrophotometer could handle that as well. But that is what they were after. Question, Sam? Okay. So that was, I believe, a point or two. Okay, that was actually 2 points there for saying the correct factor and for answering it in that fashion. And if you can use a formula, that'd be even better. Okay, last and not least for F, explain how the experimental data indicates the reaction is first order. I had so many people say there's a linear line. The amount of stuff is going down. Did you plot it? If you plot it, it's not really a linear line. Okay, in fact, if you were to look at this line, okay, it would look something like this. But we don't ever plot the concentration or absorbance over time. If I don't want to know if this is first or second order, okay, I do one. Actually, it probably looks like this. Sorry, but the point is, you don't know if it's linear by just saying it's linearly. It's going down. Okay, is not good enough because if it was second order, it'd be going down too. Anytime you have initial concentration, which is related by the absorbance, the more stuff you have, A equals ABC, right? High A. And I'm going over this because you could see ABC questions again. All right? We didn't spend a lot of time on it, but they did. So they're telling me this is something you should know how to do, and it's not that hard. But you need to understand now in rate, whether it's the concentration or it's the A, it's synonymous, right? A is equal to what? ABC, this is a constant, this is the path length, so these are essentially what? Proportionate. You can't look at this and say it's going down. The only linear thing you must say, and Sophie, you said it correctly, because I think you're only one, okay? Sophie said if you do, and she wasn't sure, but she just went there and she was right, if you do the what? The ln of the concentration, okay, it would be linear. She didn't prove it, she just said it, and she's right. You just can't say it's going down linearly, because you're going to need to tell me about the what? The x-axis. The concentration over time is going to look like this. Second order would look very similar. Now, what's different, and what they were asking for was not to say it was going down, because they're not going to accept the question to go down because, of course, it's going down. They're never going to give you credit by looking at data and just saying, oh, why is it first order? And you would say because it's going down. They would never give you an answer for that. It's going down because, what do we know about first order? It's linear and negative if it's the ln of the concentration, right? Something else you need to remember, that the halving per time period stays what?
Consistent.
Constant. The half-life will be constant. They love to pick on first order and have it, put a star around in your notes. So if you said the halving time periods, and guess what? Don't we have nice halving spots here? You could have compared these values to themselves, and this is about half of this. So you could have said the halving time periods stayed constant. That does not mean this is linear. If you were to plot this, it's not linear. Okay, even if it was, the linear of the concentration, or A, is not how you figure out something is first order. It's that the halving periods stay constant, the half-life stay constant, or the ln of that would be linear. That's what they were looking for, not just to say it's first order because I see the graph there. It's not. You just can't say that. Okay? So that's why you may have said something that was almost right, but I could not accept. Neither could any AP reader. Yes?
You said we can't take this home?
Yes, that goes home. I want it back. You take all that. The reason why I work so hard to get it done is I want you taking home. I want you to know walking out where you stand, how close you are.
But you still want this after
I want it back. I want it all back, because this is your final. I have to put it on the file. But that, okay, is something I want you to study from. Okay, yeah, you take it. Okay, next. And of course, for Sam, you had no reason why they was this all these here. It was like, wow, okay, sounds kind of silly. Okay.
So you can't see the next question?
I'll tell you how much fun that was. I'm like, oh god. Okay, especially when it's like the 27th one, right? Okay, KSP values for, oh, there's a question above. It's A. Let's do that. Let's be crazy and go in order. Okay, now this got me nuts. Okay, not that, where did my pen go?
Not that your life
Now listen, answer the following question about iron and aluminum compounds. Iron oxide, aluminum oxide have similar chemical properties.
Some similarities due to the oxides having similar lattice energies.
I should have taught it. They want two reasons why the lattice energies of the oxides are similar. Okay, for the millionth and one time, they seem to be loving to ask this question. Not difficult. What do we know? We know that Coulomb's law is in charge here. And as I've been saying, charge density, you guys can say it many ways. What do we know? Coulomb's law. It's the charge over the radius squared, yeah? So Coulomb's, which is the charge of attraction between the two ions in my crystal that make it hard for them to be pulled apart, is equal to the two charges involved, so the Q of 1 times the Q of 2, over the radius squared. And what this means is, when I increase the size of the charge, I can do so by increasing the size of the individual charges. So why would they have similar lattice energies? Number one, they both have the same charges. Iron, and you should be able to do this, Fe2O3. What's the charge of iron? If this is -2, -6 overall, the whole thing has to be what? 0. So this is +6. There's two irons, give me +6. Each iron is +3. And for the same reason, so my friends in chemistry, we're dealing with aluminum +3 and iron +3. For the same reasoning, when I do aluminum 2O3, you come up with +3 for the aluminum. So the first thing you would say is they both have the same +3 charge. And a lot of people said very well, they both have the same oxidation state. So that was good, you got the point. Now, the next piece, I need the second piece to Coulomb's law, the second piece to this. How big are they? Well, if they're similar, and if you notice, okay, it's hard to understand iron and aluminum, but you'd have to make the guess that the radii must be also the same. By telling you they're similar, you had to assume not only the charge is the same, but the radii. Because if one was so much smaller than the other, wouldn't that make one different charge?
But Fe's like twice the weight of.
That's not about weight. It's not about weight. Okay? Look at sodium. What's atomic mass of sodium?
22.99.
Great. What's atomic mass of argon?
39.95.
Who's heavier?
Argon.
Who's smaller?
Argon.
It's not about molecular mass and atomic radii have absolutely no, correlation. Okay? It's about the attraction of the electrons and how many filled subshells you have. So they have to have the same radius. Those are two easy points. I pounded that in that one test. It keeps coming up. It keeps coming up. In your multiple choice questions, how many times are they listing the radii of the ions and the charge? And they want to know who's got the greatest lattice energy. Why do they stick together? I've been talking about all year charge density. If you've got a high charge and a small radius, by saying high charge density, you're saying, okay, big charge, low radius, big attraction. Okay? So that's A. 2 points there. Okay, next question. I got my compounds. Ooh, a little bit of KSP. This test didn't have much. I'm expecting your test to have something. Who knows though? Okay, that'll be the fourth example. So here we go. The KSP values for iron oxide, aluminum oxide are given in the table above. A 1 gram sample, a powdered sample of each are mixed together and placed in a liter of water. Well, these are incredibly small KSPs. What do we know about a KSP? It's an equilibrium constant. Products over reactants. If my K is small, who's favored? The reactants, which are the solids. So there's very little free ions in water. These are very, very insoluble, which makes sense. I'm +3 hooking up with a -2 in a crystal. Water can't compete for those charges. Which ion will present higher concentration? And you guys did a nice job. Okay, now some people got lost in the sauce here. Who has the higher K value? Yeah, the one with the lower negative is the one closest to 1. Now, in the rubric, and I wasn't at the AP grading for this, they said that you had to say, supposedly, that aluminum oxide, because it has the same what? It has the higher KSP, and then they said has the same stoichiometry. But I don't feel like that's something I can live by. Of course it has the same stoichiometry. They have the same what? Ratio of stuff. So I didn't think that was necessary. So you'll see that, in my opinion, I think they should have, and I don't, the people can argue with me if they've been at their AP reading who watch this video, but I accepted just saying that this one, of course, has a higher KSP, more ions. They have the same formula, so why would the what? Stoichiometry be different, okay? But just pay attention. If it was another test, okay, and they gave you the reactions balanced, and these guys had different ratios, this being iron, or let's say copper 2, that'd be copper OH2, you couldn't directly compare them. You'd have to figure out, like it's a 2-to-1 to a 1-to-1. Because these are the same ratios, okay, when they dissociate, all right, into the ions, then that's fine. So that was a pretty easy one.
Are the AP graders teachers?
Yes.
Like
Most of
teachers
them,
of the class?
most of them, yes. Okay, most of them, yeah, absolutely. But there are definitely professors and stuff, and they have people who've been doing it for 20 years. There's like a whole organization of like head grader, like there's a chief grader, and everyone grades. There has to be someone behind regrading to see if that person is staying. It's a whole huge process.
Do you like different?
No, I don't go because I usually have other tests to prepare for. I would love to be involved with that, but I'm not.
Do different people if you're a person grading it, do you only grade one question and then
You become very good in a question, but someone else is checking your work for accuracy. You're working on a table. It's like these tests get manhandled by so many people and checked for. Oh, that person's falling off. You have to check him more. Like there's so many back checks. So your test gets looked at by many people to make sure for absolute accuracy. There's no holes in the process. They work for like 4 or 5 straight days, and it's a conference. Any case, which right of balance chemical. Now this was bad because people didn't know what dissolution meant. Okay, dissolution means mixed with water.
I did just assume. I thought it was distilled. I didn't even read it right.
No, so that means all this means you're putting water. So if you said aluminum oxide, all this was what? OH3 solid breaks apart into the what? Aqueous aluminum +3 hydroxides, aqueous. Now you can put solid here if you like. They wouldn't correct it wrong. They wouldn't make it wrong without the charges. Okay. You certainly could have done what? How these became an oxide. Okay, so you could have showed how this was you could have done this in water going in reverse. Was the answer too? So the answer was there, but it meant this in water produces the hydroxide. So you allowed this solution is in water or this. That was 1 point. Okay. All right.